Okay, lesson 12.5, we're seeing something very interesting. For the first time in recent sections, at least, our terms can be negative. But very, very, very importantly, today, even though you might have negative terms, they will be alternating. Going from a positive term to a negative term, then to a negative term to a positive term, always changing from plus minus to plus minus or from minus plus. Notice how we represent that. Look at the formula, look at sigma. I've highlighted that inside of sigma we'll have negative 1 raised up to the n minus 1 power. As negative 1 is raised to an even power, it turns into positive 1. And then as negative 1 is raised to an odd power, it will, of course, be negative 1. You can change your counter, as we'll see later on, but notice your power up here, instead of having n minus 1, look what would happen if we just started with an n, starting with our counter of n equals 1. You could begin with something negative and then go to something positive. So here's the most important thing that you need to know. If you have an alternating series, you cannot use the basic comparison test. And you cannot use the limit comparison test. And you cannot use the integral test. All of those are working under the assumption that you have a positive term series. What you have instead is the need to have a new tool, a new test, and that's where we're going today, the alternating series test. The alternating series test is actually very nice and short. You don't have to deal with a comparison either. I think that can be very appealing. Let's suppose that you do have an alternating series where, of course, you've got a formula for b sub n, which would determine your terms, but the negative 1 is raised up either to an n or an n minus 1 power in front of that. Ignoring that negative 1 to the n just for a moment, just looking at your b to the n formula, if you can show that your series is decreasing, if you can show that b sub n plus 1 is less than or equal to b sub n, that's your first condition for the alternating series test. The second condition says, now take the limit as n goes to infinity of b sub n, and if you arrive at 0, meeting both of those conditions, then you can say that the series is convergent. So meet those two conditions, and you're done. Now that's fantastic. Notice what I've put off to the side here. I've highlighted it in green. I put in 4 little stars here. This is the big misuse of the alternating series test. So very often kids will think, oh, if one of those two conditions fail, then I'll say by the alternating series test, my series diverges. Notice what I'm saying. The alternating series test never, ever tells us if a series diverges. It can only tell us if a series converges. To speak about divergence, we're going to have to do something a little bit different, and we'll see that in a moment. But look, with no further ado, let's see where we're going with this. Look, you've got this formula, 1 minus 1 half plus 1/3 minus 1/4. Very clearly looking term by term by term, I think you can see that we are alternating. But looking at sigma, hey, this is delightful. You can say, looking at sigma, hey, I can see a nice formula. This is known as the alternating harmonic series. The alternating harmonic series. It looks exactly like the harmonic series, except you just change sign for each and every other term, I should say. So you'll go from a plus term to a minus term and so forth. Now, what would gut instinct tell you? Do you think this series would converge or diverge? You know, over and over and over again, we hear harmonic. We think divergence, don't we? Well, we don't know. Maybe it will converge. Let's see. Condition A, can I show that b sub n is decreasing? Now, there are two ways you can do this. By the way, haven't you done this recently, even yesterday on a quiz, showing that a function is decreasing? How do we do that? Take a derivative. You could say, well, look, b sub n clearly is 1 over n. Let's just take a look at f of x and pretend that it's 1 over x. Take the derivative. What's the derivative of 1 over x? Negative 1 over x squared, which clearly is negative, right? For x values that are greater than or equal to 1. Therefore, b sub n plus 1 is less than b sub n. My function is decreasing. That means term by term by term, I will be getting smaller. That's condition A. Let's look at condition B. We're going to take the limit as n goes to infinity of b sub n. And we could say, well, let's see, the limit is n goes to infinity of 1 over n. Where's that going? 0. Guys, I've met both of my conditions by the alternating series test. This alternating harmonic series converges. It goes in the exact opposite direction that gut instinct would tell you. As soon as you even begin to think about harmonic series, you might think, well, certainly this must diverge. Yes?
You made b sub n.
Yes.
So just choosing like the most logical.
No. To get b sub n, notice what's happening up here. B sub n, I just want to point out to you this. Maybe this will help us out a little bit. Look up in the very beginning, right up here. In my sigma, I've got negative 1 to the n power times b sub n. When I'm looking over here, here's my negative 1 to a power. What is not there? What is also there aside from that negative 1? Imagine that that's not there. What's remaining is your formula. It's 1 over n. You see what I'm getting at? So ignore the negative 1 to the power of n or n minus 1. What remains is your b sub n formula. So look, as soon as we jump to number 2, just immediately, what's b sub n for number 2? 3n all over 4n minus 1. Okay? And that's where we need to go. Now, gut instinct might tell you something. You might think, now wait a minute. What's the limit as n goes to infinity of that thing? 3/4. Uh-oh. I'm not meeting my condition for the alternating series test, am I? So I cannot use the alternating series test. To be able to do that, I have to show two things. First, that your b sub n is decreasing, that b sub n plus 1 is smaller than b sub n. But second of all, just as important, this limit has to go to 0. So, wow, I can't use the alternating series test. Here's what I can do. I can say that the limit as n goes to infinity, let's throw that negative 1 back in there, negative 1 to the n minus 1. Would you agree that this thing would be bouncing around from 3/4 to negative 3/4, depending on whether we'd have a positive power for negative 1, an even power for negative 1 or an odd one? So this thing doesn't exist. Negative 1 to a power, if you're at an even power, you're at positive 1. Negative 1 raised to an odd power goes down to negative 1. But does not exist means that you're not equal to 0. Guess what one of your best friends is in terms of quick checks if a series converges or diverges? The nth term test. By the nth term test for divergence, by the nth term test, this original series diverges. So notice I'm not saying by the alternating series test. It's the nth term test that you would use if you're going to justify why a series would diverge. The alternating series test can only be used to show or prove convergence. Okay, yes?
So I just use the nth term test if I don't know what your series goes to.
Well, as long as this limit doesn't go to 0, then the game's over by the nth term test. If it is 0, it's indeterminate. We have to have further investigation. Okay, so that's the key. Okay, we doing okay? All right. Well, here's the second half. It's almost like a second part here. Alternating series estimation theorem. Let's assume that we do have convergence. In other words, we meet our two conditions. We have b sub n plus 1 smaller than b sub n. And my limit is n goes to infinity and b sub n goes to 0. You'd say, well, hey, that means my series converges by the alternating series test. Yes, but let's talk about error. Look, S right here is the true sum. S is the true sum. S sub n is the nth partial sum. So look, if you stop at the 10th term, adding up the first 10 terms, obviously you won't get the infinite sum. So what that means is this thing right here is the difference between the true sum and your approximate. This is what we call our error. So whenever we're talking about error, we're saying take whatever your true sum is. By the way, you might not even know what it is. 99% of the time you don't. And you'd say, well, look, I know you're going to converge to something. I just don't know what. If you'd say, what if I just add up the first 100 terms? How much am I off? What's my error? This is so bold. This error is less than or equal to the n plus 1 term. The n plus 1 term. So this is unbelievable when you think about it. I think it's very important for us to have something like our alternating. Let's go back to example 1, where we had this formula, -1 to the n minus 1 all over n. And I said, hey, let's add up the first 10 terms. We could do that, right? We could add up the first 10 terms. So this is adding up the first 10 terms. You'd say, I wonder what my error is. Obviously, if I do that, I'm not going to get the real sum, right? Guess what your error is? It's less than or equal to your 11th term. It's less than or equal to, plug it in, you'd get 1 over 11. You'd say, hey, if I stop there, I'm guaranteed I won't be more than 1/11th off of the real sum. Okay? So that's pretty bold. If you were going up to the first 100 terms, you'd say, well, now I'm going to have to go out to my 101st term. It'd be 1 over 101, where I could say, now I know I'm that close. Okay? So what we're going to do next is talk about a way to measure decimal place accuracy. And if E is the error in the approximation will be considered accurate to k decimal places if you have 0.5 times 10 to the negative k. I think our video is going to stop here.